everybody. So today we're going to start programming actually a model, work on a message classification or email classification, I guess. Well, it's really text messages, very short. And we can see this is the training data I have here. And we have the label and we have the message. So these are all text messages. And then the label ham means that it's a good text message, and spam means that it's a bad text message, someone is trying to do something malicious. So now we're going to create a model to actually identify if it's spam or ham. It's going to use binary classification, and we're going to have 1 for spam and 0 for ham as our labels. And we're going to basically encode all of these texts using vectorization, and we're going to be using doing everything from scratch using TF-IDF, that algorithm, and also just gradient descent. So we're going to use NumPy. Of course, NumPy is always needed for making models. We're going to use pandas, which is also important for data handling. And we're going to use re for regular expressions. And we're going to use pickle for actually saving the model. We're going to save the model as a whole instead of just the weights. And then we're going to use matplotlib for training. Matplotlib.pyplot. We want to make sure our loss function, we want to make sure the model is learning correctly. And now what we want to do is first explore what TF-IDF is. What does that do? So it's basically a vectorization algorithm. And I have like a presentation on it, so it makes it a bit clearer. That's right here. It gives you a score basically. And I'll explain what these mean. Term frequency is basically how frequent a term is. And inverse document frequency is a bit more complicated. It's like how frequent a term is in the documents, but compared to all the other documents. And you want it to be very unique, so it's basically the inverse of that. So let's first look at term frequency. And our goal is to determine how frequent the word is in a specific document, in a single one. And we're analyzing only one of the. So we are going to let t represent the word, for example, and we're going to see this. The term frequency function will be the count of words t in the document divided by the total words. It gives us the frequency of the word t in the document, and a document can be anything like a single email or customer reviews. We're going to be having a single email or a small email, which is a text message. So now, the one that's a little bit more tricky, but also very important, one of the most important parts of this, is the inverse document frequency. It's going to be really what differentiates things like the from like any word that's more important than the or is or a. Those words that are just transition words, those appear a lot in documents, but it's in every single document, so we don't care about that. This vectorizer is not going to assign any importance to that. So basically, document frequency is how frequent the word is in all of the documents we have for our training data. And then it's given by this, the number of documents containing that word t, divided by the total number of documents. Again, it's like intuitive like this, right? Like a frequency. And we take the log of it, so the number of documents containing t is equal to the total number of documents. Well, this is an example of why we're going to use this, so then the IDF will be equal to 0. If that's a bit confusing, I'll explain that. We're basically going to invert this df, so it's going to be 1 over df, and we'll have total number of documents divided by number of documents containing the term t. So if you see here, what is going on in this graph, hopefully will make you understand it better, what's going on with this function we have. You can see how the function behavior is. It starts at undefined. Because of 0, it's not possible to have t in 0 documents when you're already analyzing t. So that's why you're not going to consider 0 at all. Probably not going to be any decimals either. It's going to be discrete. So we don't really care about all of these decimals here, but 1 and then 2, 1 and then 2, 3, 4, 5, 6, 7, 8, 9, 10, and then it's not possible to have t in more documents than the amount of documents you have. So we're really going to be analyzing from 1 to 10 discrete. And it makes sense, right? Because if x gets bigger, then you have T in more documents. And that means that it's more popular, and it could be like it could be a transition word like the or is. That's not even important. We don't care. We want it to be unique. So it makes sense to be decreasing because you want it to be unique. So I hope hopefully that gives you a good intuition for why the formula is like this. So then if you can also see that here, if x is equal to 10, and we have 10 documents, it's going to be 0 because then we don't care about it at all. It's in all documents, so it's probably just going to be one of those transition words. Now, with TF-IDF, we're going to measure them both together. And that's basically what this is, just multiplying them, element-wise multiplication, not a dot product. Because, let's say you have U1 and guaranteed, both are like important words, right? You can already tell. U1 appears in many spam emails. Not too many times in spam emails. Sometimes it could be, but usually it's not that many times. So it has a low TF, but a high IDF, because of it usually is only in spam emails. Then guaranteed appears a lot of times in an email, but can be in both spam and non-spam emails. So it has a high TF and low IDF. Now you can see how these are going to coincide, and now the words are going to be of similar importance. Low TF, high IDF, and then high TF and low IDF. So that's just why we measure them both together. We call it a joint frequency or joint importance of the word, like similar to joint probability when you're simultaneously considering two probabilities and basically like that. So that's why we use multiplication. Now let's actually start programming it. We have all our packages now. Let's start actually making the class TF-IDF. This is just object-oriented programming we're going to be doing. We're going to create the constructor, and it's going to take in the documents that we give it and use pandas for that. And then we can now make our documents instance variable, and then we can make our tokens. We're going to start tokenizing, and we're going to use re for this. So we got to see how to actually tokenize. I'll go and show you regex 101. Okay, so let's see how to use regex a little bit, at least enough to be able to tokenize. So if we have a word here, like hello, my name is Ryan, we also have this, like you can see all of them in here too if you're lost sometimes when you're reprogramming more. We want to, let's say we have some capital letters. We want to take capital letters, and then you can put some numbers in here, whatever. Maybe you can have a phone number. Now, we want to take capital letters, so A to Z, and we're going to take lowercase from A to Z as well, and we're going to take numbers from 0 to 9. We're going to put these in brackets and look at it. We got all of these letters, and we got numbers as well. And we're only getting these specific letters. We're not getting words. But when we tokenize, we want to get words. So this is not what we want. And we can see here, everything is written here. If you have more questions, you can see it here. There is some symbols here that gives you going to look for more than one occurrence. That's the plus symbol right here. It's one or more of A. So if we add a plus here, it's going to give us all of these until the next space, because the space is not included. So you're going to see it's going to be like this. But we're going to include A to Z capital, but we're going to lowercase it after, because we want our model to be non-cased, because it's not too significant. Maybe it is when you have a LLM, when it has to write sentences and needs a capital letter. So this is what we can use. We can also try to get dashes for phone numbers. If you have something like this and you have like some dashes here, then you can get it using this. So now it's going to get the dashes as well, and that's what expression we can use. Actually putting it for the program, I'll copy this. We can use re.findAll, and we're going to import that expression that I just had. We're going to look for it in the document, and we're going to ignore the casing, so our model is uncased. And we're going to make this a list comprehension by doing this, by having the document. This document is like the comprehension variable, and we're gonna have that document in for document in documents. So it's going to be a specific document in all of the documents. You can think of it as our training corpus, our pandas data frame with all of the documents in there, all of these messages, like this one, all of these. And we're just going to be looking for one of them in all of them. And we're going to go and make the tokens like that. And it's going to be a list of those. And now we can test this by making the vectorizer. And we'll set it equal to the TF-IDF. We'll make that documents variable. And then we're going to read the CSV file. This is just how you read the CSV with pandas. And it's called training data.csv. I'm going to make sure the encoding is correct. So let me make sure that. I'll go and print the document so we import it correctly. I'll only print the first 5 lines. I did not even declare that yet, so it's okay. Okay, here we have this. It's working. Now I'm going to go and give the documents into here so we don't have error again. So, because if it's looking for documents as a parameter. And now we can do vectorizer.raw tokens. So we can see the tokens of this vectorizer object. So basically, raw tokens is an instance variable of vectorizer. It's a we can access it using vectorizer.raw tokens because vectorizer is an object of this class, an instance of this class. So now we will print this out, make sure that it works. Okay, we got it to almost work. We just forgot to only include the messages because we don't care about the labels right now. So we're gonna have the message. And we have lots of these. We see like so many raw tokens we have here. It works. We have like lists of lists. It's very hard to see. These are all for each document. So you can see how these lists are separated like that. And all of these words are in there. It even got the numbers. And I did not lowercase them, but it did ignore the casing if it's capital. I don't really think you need that even because we have A to Z there capitalized, so it doesn't really matter. But I just kept their redundancy. Now we want to lowercase everything because we don't want to have like this capital X's and we don't want to have other capital things. So we're going to make the self.tokens variable, which will have all of the tokens lowercase. We're going to make basically a list of the raw token, the lowercase, so it's going to be lowercase. And then we're going to do it. We're going to make another list comprehension, and it's going to be like a 2D list kind of, because this is already a 2D list. You can see. So we're going to do that for raw token in raw tokens, and we're going to do that for raw tokens in self.raw tokens. So it's going to lowercase each of the tokens in the individual list, and it's going to do that for all of the lists in the whole raw tokens, self.raw tokens variable, which contains a 2D list. So now we can see the tokens. All of them are lowercase, so that's good. That's what we wanted. Free is now not capitalized anymore. Let me just have some placeholder functions for now. The TF function, and I'll pass right now. And we'll have the IDF function. I'll pass that. Or maybe we should actually start making them, both of them, and then we'll make the vocabulary, because we're going to rely on those for making the vocabulary for training the model. So first, let's actually start with the TF function, the term frequency. We first need to make our total counts variable, because we're going to look for the counts in each document. And then we're gonna basically have 2 counts variables. One counts for the document, and that's going to be cleared after we look at the document. So let's say we have this document, or let me look at a document. You can see, or well, they're very long, these documents. So here's an example of a document. It's relatively small. We're going to basically count how many times I appears in this document. It will be 2. You see I is here and I is here, and then M is maybe 1 time. Yeah, it's only once. So we're just going to have the counts for that, and we're going to do that for all of the documents. So that's why we're going to use total counts, and then in there we'll have some dictionaries that has the word, and then it's going to have the count. So we're going to have that counts variable. It's going to be a dictionary. So it has a key and a value pair, and we're going to go for tokens in self.tokens. And let's go and see if, first what this is gonna be. This is gonna give us each of these documents. That's what it should give. Vectorizer.tf, and we don't need any argument for that. And it's going to be okay. Yeah, so we got each of the documents like that, and then for token in these tokens. So now it's going to look at the individual tokens in these documents. So the individual ones like you, are, awarded, and those stuff. And then we already know it's going to work, so it's no use doing that. Now let's check if the token is in the counts variable. If the token is in the counts variable, then the counts of that token key will have a value that's now 1 greater. So it's going to just add 1 to that key value pair. And then if it's not true, then we're just going to create that key value pair, and it's going to be equal to 1. It's just our starting value. So now that means that, let's say we were looking at this list right here. We were looking at this, and we saw, like, we're looking at one of them. If this is in the counts dictionary, then we're just going to add 1 to it. If it's not in there, because it's obviously just the first thing, so there's not in the dictionary, it's empty. So we're just going to make that key equal to O, and the value is going to be equal to 1. So that's basically what it's doing. And now we're going to append that. We're going to append it to total counts. We're going to append the dictionary to there, so then now we can clear that dictionary and then do the next one. So then we don't depend on the other documents. So then it's going to be for each document, each unique document. And we're going to set it to nothing, so it's going to be empty. And then I'm going to return this. Let's go and see how it's going to be. Return total counts. Print this because we just returned it. So now let's check total counts. Forgot to print it out. Okay, so here we have it. All of these documents now have counts. Now we just got to divide that by the length of the document, so we get the term frequency for each one. Let's go and actually return the right term frequency, because that's what we're doing. We're not just returning the counts. So we're going to have a variable with all the TFs, all the term frequencies for all of those documents. It's just like the total counts variable. It serves the same purpose. So we're going to have the TF dictionary, and we're going to loop through the counts, total counts variable. And it's like we're doing the same thing. We're looking at each dictionary in the total counts variable. And we're basically going to have another list, or really like a dictionary comprehension. And first, let's see, let me test something. I'll check the sum of the counts values to make sure that it has all of the words. It should have all of the words. If, yeah, let me make sure that if I do this, I'll print the sum of the counts values. That should be the total counts. We'll make sure that is the total counts. Okay, it does that for every document. That's correct. Now we can actually make the comprehension. So now TFs will be equal to the K, which we're going to update with the new V, which is going to be the old V, divided by the sum of the counts values, divided by the total counts. And then we're going to do that for KV in counts.items, which is going to contain the k and the v, obviously, which is the keys and the values. And that should work. Make this a capital TF, because that's what it's defined as. And then we're going to append that to the total TFs. And as you can tell by what we did here, we're going to clear the TFs variable. So we do it for each document, so it doesn't depend on the other ones. And we're going to append it to, we're going to append TFs to it. And we're going to clear the TFs dictionary. And then we'll return the total TFs. Okay, we got it. So these are all of the scores, all the term frequencies we have here. If you have any questions, you should leave a comment. And this is basically just the algorithm. It's not too complicated. And now we're going to do the IDF, which is more complicated. It's a little bit tricky to do this one. It's not as easy as that. So we're going to have the counts variable. Again, and now we don't really care about each individual document. We care about the entire corpus of documents. So we're going to have a unique tokens list to contain all the unique tokens. And we're going to loop through the self.tokens variable. And it's going to give us each unique, each document. And we're going to append basically the unique tokens to the unique tokens list. How are we going to do that? We're going to make a list of the unique tokens, which is the set of token. And the set function basically gives us all the unique values. After doing that, we can now loop through the unique tokens. We're going to go through, we're going to use I as an index, so we can actually do indexing. And we're going to use that for the token in the unique tokens at that position I. And if that token, it's a token in the documents, because you see that this whole thing is a list. We have a document, we have documents in there, and the document contains the tokens. So we're going to see those tokens, and we're going to check if those tokens are in the counts dictionary. And if it is, then we're going to increase the counts of the token. We'll have increase the counter by 1. Else it's going to be equal to 1. We're going to set that key equal to 1. It's basically the same thing we did here. And now we can make sure that this is working. If I return the counts variable, we'll check if that works. I'll do IDF here, vectorizer.idf. And we got all of the counts here. For the entire document, we're going to see the unique counts for an entire document. That's why you see some of them are 71. That's how high it is. It's like very high. We're going to actually make that score. So we have to use the log, and we have to use that dictionary comprehension again. And we're going to basically take that log using np.log. And we're going to look at the length of the self.documents. If we see here, I'm going to make sure that I'm doing it correctly. It's the presentation. Right here we have the log of the total number of documents. That's why it's the length of that. And then we're going to divide that by the number of documents containing the term. So that's going to be the length of documents divided by v, which is already there, the value is the counts, for key and value in counts.items. Same thing as before, like that. Just the same dictionary comprehension, and we're going to return that. And we're going to return IDFs. And notice how in here, this whole thing is a dictionary. So that's why we didn't have to do this mess right here. We didn't have to actually go through each one like that. We already have all of it in a dictionary. It's not like a list of dictionaries. It's just a dictionary. So we got our IDF and our TF initialized. We got those functions. Now we can make our vocabulary. So now we have TFs. We'll go and make our TFs variable equal to self.tf. We can use the function inside the class using self.tf for that object, and we'll have IDF equal to self.idf, and we're going to make a TF-ID. I'll just use that because I'm running out of variable names, and it's going to be a dictionary. And basically, we're going to multiply these two, element-wise multiplication. So that's why I'm just making this dictionary. So it can contain the key and then the value, the score, TF. So the IDF times the TF, that's going to be contained in this dictionary. We're going to go for TF in TFs. Because remember that TF is actually, we can see that it's actually a list. If I do this, let me go and just comment this out so it doesn't have an error in case it does. You see that TF is actually a list here. We see that this bracket tells us it's a list of dictionaries. So we're going to have to do for TFs and TF. For TF and TFs. And we're going to go for the key and value. We're going to go for that. We're going to do that. So then we can actually use that value. We don't really care about the key, but we'll go for that value. And we want to make sure this key is the same as the key in the IDF. So then we can multiply the IDF's value by this TF's value. So we're going to look for if that key is in IDF, then we can compute that score for TF-ID. We would store it in TF-ID as K, which is our key. And that's going to be equal to the IDF's key, IDF's value, which is going to be given by that, times the value, times which is already in here. And then we can make that self.vocab variable and assign TF-ID to that. So now our vocab variable should be correct. We'll have all of the unique vocabulary with all of the scores, TF-IDF scores. So we will print out vectorizer dot vocab. Should work. And we have vectorizer.vocab here. Everything is printed out like this. And we see all of the scores, and we have all of the keys as well. And we can see the length of this. See how big this is? It's 8861, okay. Now we're going to actually train. We're going to start training the model. So we actually have our TF-IDF, we didn't actually make our combined TF-IDF for the training. We just did it for the vocabulary, so let's just make that. Now TF-IDF, let's just do this name, TF-IDF self, and that will be, it won't be too hard because we already did the hard part here, so we can just do this quickly. We'll make this using TF-IDFs again, TF-IDFs, and we'll set that as a list. Oh, I forgot to put a def here, sorry about that. So we're going to have that as a list. And we're going to do element-wise multiplication. Again, we're going to have the TFs. TS will be self.tf. We're basically going to do the same thing. So IDF will be equal to self.idf using those functions. And then we're going to go for the TF in TFs. Each TF and TF, so we're basically going to compute the score for each of the documents compared to the others. So we're going to have TF-ID equal to dictionary here. And we're going to compute that like this. We're going to use the same key value in TF.items. And in here, make sure it's TF. So TF.items. And we're going to look for if that K is in IDF. Then we'll make that list have that value for that key. So it's basically that same thing times value. That to this list. because now we don't want to have, now it might be confusing why we're having this TF-ID here. I'll show you now the reason why we're doing that. We can see first TF-IDFs. You can see this if we do print the vectorizer dot TF-IDF. We'll see what happens. It's going to be a list of the dictionaries again. See, it's going to be a list of all these dictionaries, and basically it's going to contain all the dictionaries, but still it's going to be computed like the IDF and TF, because we're not going to contain the unique documents. We don't care about any unique words. We're going to have each document like this. So then we can make a data frame of these, and then we can make that a vector, or really it's going to be a matrix for all the input features. So we're going to contain this in the input feature matrix. First, we can convert it to a pandas data frame, so it's easier to work with and actually look at it and get all those categories. So we'll do p.dataframe of the TF-IDFs, and we'll fill, well, let's go see what it is first. So we'll have so we'll now make this data frame, pandas data frame, using pd.dataframe, and we'll make it of the TF-IDFs. And let's go and return this to see what it is. TF-IDF, TF. It's going to give us like everything organized. And we see it here, lots of non-number values. It's going to, this is why we are using pandas, because we get all of these indices here, and we get the columns as the number, and it's going to give us the scores as the values. And we see all of these not a number values. We want to replace that, because we're going to put that into NumPy. So we're going to want to replace that, fill those with 0. It should be 0 there. We see all of these zeros here, and that's actually going to give us what we want. And now we can convert this into our matrix by putting it through NumPy. We just make it called the matrix, and we will have that TF-IDF df.toNumPy. It's going to allow us to have that, and we can just return this TF-IDF matrix, and it should be give us the NumPy version of it. We just used pandas as a, and I didn't spell it correctly, but yeah, we're using pandas as a middleman to actually get us there. Make sure you have an underscore, then it will work. But there it is in NumPy. If the score is 0, then it's basically not important. Those are all like transition words. So now we have our TF-IDF score, we have our IDF score, we have our TF score, and we have our vocabulary. Now we can actually make the model to train it. And first, let's create a testing and training split, so we have that out of the way. We can make our size. We'll have it like a 80-20. So let's just make it an 80-20 split. So we'll have the size as the length of the documents of message. Let's go make sure we have that in string. Okay, there we have it. And now we'll change this. We'll have it as, we'll have the train. We'll make a train variable for training documents for the message column, and we're going to index that at before everything. For the size, we're going to cast it to a int. We're going to multiply basically the size of the document times 0.8. So now we're going to get 80% of the document. We're going to get the index at 80% of the document. We're going to make that integer. So then we can actually index it. We can index double values or floats. So that's why we do that. And then we want to get everything before that. That's why we're using that colon there. And now we also want to make our labels. So make sure we have our labels as well. So the label is equal to the documents of the label. Make sure we have the label here. Label. And we're going to do the same thing. We'll have, it's for the size, int size times 0.8. So it's going to be for the same, it's going to be the same size as the training, because we're going to compare them. basically for our y hat I as our prediction, and then we're going to have yi, which is a label. We'll just have that get the training data. We can make like a testing data set later, probably. We can check that out. But now let's go make our input feature variable as vectorizer.TF-IDF. So it'll contain all of those score. It's going to be a vectorized now data. So that's what we were doing all along. We were just vectorizing the data. So it prints out x. Make sure that it was having all of the data vectorized. There we have all of the data. We have those keys, and we have the values. Okay, now we're going to make a mapping for that message, because we don't want to have spam and ham. We want to have like 1 and 0. So we want spam to be 1 and we want ham to be 0. So we can make a function that does that. It's going to be 1 if x is equal to spam, and else it will just be 0. So it's going to handle that for us, and we can make we can use the map for that. We can have y equal to the list, map f to the label. So let's check if that works. Let's print that y. It should give us, just make sure I spelled it correctly. Okay, so it's going to map the function to the label, and we have all of these. It's going to be our actual y variable we're going to compare it to in the loss function. So now, let's go make a class for logistic regression, because we're going to be doing logistic regression, and we're going to make a constructor again, and we're going to be having the input features, and we'll have the weights, and we'll have the actual labels, there, and then we're going to make our instance variable y, that's the y, and we're going to have our weights, and then we're going to have our input features, and then we're going to have a loss history. So then we can check actually the loss curve using matplotlib. So let's go ahead and do this. This is now real machine learning business here. So we can make our sigmoid function. We know what sigmoid is. We have a z value, which is a linear combination or a linear transformation vector. Basically, it's just a dot product. We're going to return 1 over 1 plus e, which is numpy dot exponent of negative z. This is just that activation function. It's you can probably search it up, you will understand it. And now we have the negative log likelihood, which is our loss function. Maybe I should show it a little bit so you understand. Negative log likelihood and sigmoid. You can see here. So the sigmoid function, let's see the sigmoid function first. Sigmoid already is defined to be like this. It's going to be this S-curve, and loss function and negative log likelihood is going to be what this is, or not. It's usually not shown like that for logistic function. We can see here these p's are the predictions and y is the actual values. So we're just going to be using this for our model, and we're going to use the sigmoid function as our activation function for making the predictions, giving us the probability that our prediction will be equal to 1. So there's like a lot of math about it and stuff. You don't really need to look at it. This is the most important thing. So now I also have a video where I derive this. If you're interested in seeing that, I have a link. You can see how this is actually derived, because it's going to take like another hour to actually derive it, because it's kind of hard to think about at first. You have to make it very simple. So now we're going to use that same formula that we have there. So first we're going to define our prediction, ypred, and that's going to be equal to the sigmoid function of our linear combination, our linear our dot product of the input features and the weights, self.w and self.x. This is the matrix multiplication operator in NumPy. And then return the negative sum. I'll just use that same formula. I'm gonna make sure I'm doing it correctly. I'll just have this So we're going to have the negative sum. We use np.sum, and we're going to have self.y, which is going to be what is right there, and we're going to multiply that by the log of the y-pred. Oh, the prediction. We'll multiply that by the log of the prediction. Sorry, it looks kind of bad right here. I'm sorry about that. That's just what this is here. And then we're going to subtract that, or really add that, because we have a negative sign here. They have a positive sign here, so they're really distributing that negative. So I'm going to have a positive sign. And we're going to add 1 minus self.y. And we'll multiply that by the log of 1 minus self.y-pred. So we're just doing the same thing exactly as we're doing here, as they're doing there. So we're just imitating that. Now I can see this, we can see this fully, and I think I did a mistake here. There we go. And we don't need that. Okay, so let's try to make our fit. Let's make our fit function. We'll use self. We'll have epochs, and we'll have a learning rate. For gradient descent, we're going to do gradient descent here. It's pretty important. So gradient descent is a little bit hard to think about, though. We're really going to use derivatives and gradient, which is using all the derivatives. So we're going to loop for all the epochs. We're going to do for I in range, or for epoch in range, whatever you want. Epochs. Epochs is one full pass. Basically in a neural network, it's a full pass in neural network, but we'll just call it epochs for iterations. And we're going to update the prediction using self.sigmoid of self.x multiplied by self.w using the same syntax, same thing that we did here. And then we're going to calculate the gradient. And basically, we don't know what the gradient is because we're doing this all from scratch. We're not using PyTorch to do this. If you are, then you can probably use auto differentiation. They have their engine for calculating the gradient, but I don't have that. So I just had to manually do it. And that's what I have in one of my presentations about calculating it. I calculated it here. We basically have it as the chain rule, and then we're going to do this. Remember that really this log is a natural log. They use natural log. They don't use log base 10, so that's why the derivative is like that. It doesn't have a natural log of 10 in the denominator, so that's why it's like that. And then we have all of this stuff, all of this simplification, multiplying, and then we have more simplification, and then it's actually this. It's just basically algebra after that. It's just a lot of algebra there, and just calculus. And now we're just doing the next, we're basically just going one by one doing the chain rule. We're starting with this, and we're doing this, and then this. So first we calculated this gradient here, and then I calculated this gradient, which is after lots of like getting it in terms of y hat and y I have a brief explanation. You're just taking the derivative of the sigmoid function, and then you're using the quotient rule. You get this, and then we're going to just set it equal. We already know that this is equal to y hat I, and we can then establish that 1 over y hat I is equal to that. So then we can find what e to the negative zi is right here. So we can substitute that there, and we can square both of them. So we can now replace this with this in there, and we can just simplify again more and more and just get that. That's really the trick, because you don't want to use this. It's kind of lame, right? You don't want to use that. It's annoying. You have to write all of this stuff out. It's very easy to just use that. Now we have more gradient calculation. So we're going to do the next, the easiest one, I guess, is just using the derivative of zi with respect to the weight, just a dot product. It's going to give us this derivative here, and that's equal to this, and we already know the derivative of a sum going to be for a specific weight, so it's always going to cancel out the other weights. You can think of like a whole series of these xi wi's, x1 w1 plus x2 w2, and you're going to see like a lot of those. It's going to be with respect to a specific wi, so that's why it's going to be equal to xi. So it's going to cancel out all the other ones. You don't care about wi plus 1 or wi plus 2 or wi minus 1. You don't care about any of those, so it's only going to be xi. And then we can just substitute everything in that we did here, here, and here. And we can just find this out. We can multiply it by the sum, and we can get that, and we can establish this as a dot product. You can notice how this is a dot product. It's of the same form. So this becomes a dot product. I mean, this can be easily used in programming right here. You don't want to use this in programming. That looks very horrendous, right? You want to use this. So we can make that a negative, or let me just show you that so we can see it side by side. We'll see that side by side in here. So we're gonna have a negative and p dot sum. We'll use, np dot product. We'll just use it like this so it's easier to see. And we'll have self dot y pred. We'll have self dot y minus self dot y pred. And then we'll have that divided by, we'll have that in, we're making sure that's in a dot product with xi, which is basically just the input features. And then we can divide that by n, which is the size of y, the label size. And then we got a mistake, I think, when I tested it. Right here, we're supposed to have TF-IDF instead of TF, whatever I was doing there. I'm sorry if there was a mistake there. X is TF-IDF, so we have this. Okay, so now we're going to make this a dot product, and we're going to divide that, or the length of y. So we're going to make sure that self.y length, it's going to work like that. So if I return the gradient, we can test this if we make our logistic regression model. So let's go make model equal to, make the model equal to logistic regression, or logistic regression class. And then we're going to have our x, our w, and our y. So our input features, our weights, and our labels. And we're going to have w as random parameters in the beginning. It's going to be np.random.rand. And that's going to be, basically that's to make some random parameters. We can make it a normal distribution using n. And now we can have it as x.shape of 1 or 0. I think it's 1. We want to see that. I'll see if that works. I'll see if we print out w. We want to make sure it's compatible with matrix multiplication with x. And x, we got to see x's shape first, and then we can do that. So we got to see x's shape. X.shape prints, and w.shape. We got to see. We got to make sure those shapes are compatible. Okay, we see this. Yes, the shapes are compatible. We want these inner dimensions to match. And now we can make that model. And we can return the gradient. And we can have the model.fit. And we'll have one epoch to just test it. And we'll have a learning weight that's 0.1. Doesn't really matter what the learning rate it is right now. 0.01 or 0.1. Looks like we're not, oh yeah, because we're doing this the opposite way. We have to do it a dot product like this. It should work like this now, because we were doing it the wrong way to dot product it. We have to do this one, because that's what we're doing here, self.x. That's what we're doing here. We got to make sure that it's compatible like that. Because of this, w is the same shape as y. So it's going to work now. That's just to check. We always have to do this shape mismatch checking. Yeah, so now let's go make that, let's go and update those parameters. We're going to use the gradientdescent algorithm, which is like a recursive algorithm. And I can show you how it is, like the gradientdescent. I'll just show you the formula so we can just implement that. It's going to be in Wikipedia. Right here. This is the formula. The gradient here is what we computed. And we have the learning rates, and we have that current parameter, and a new parameter we're computing, and that's subtracting that. Okay, so we see that here, self.w, which is going to be updated by subtracting the previous one and multiplying the learning rate times the gradient. That's basically the same thing as here. Now, we can append, we're going to append our loss function to our loss history after doing that. So we're going to append it, and we'll have the self.nll. So this is going to be that value there after completing a full epoch. Now we're done basically doing everything. We finished the epoch. We're just going to append it to the loss history. And I didn't have .append here. Okay. And now we're going to print out the epoch and the loss so we actually know what's going on. So it's not just blind. So we will have I, if I is divisible by 100, we're going to have lots of epochs. We'll print it. So every 100 iterations, it's going to print out a format string epoch is going to be I. The I gives us the epoch I, and then we're going to have the NLL and self.nll. So we'll have the epoch as I, because that gives us our epochs, and then we'll have the loss function, and then this is basically going to be the fit function. We have it. And now we want to make our plot loss curve function so while we're training, so we don't have any problems with that after, because you don't want to train it first and then try that again, because it takes a long time to train. So we'll do plt.plot self.loss history, and we'll make an X label as the epoch. We'll just basically do the negative log likelihood versus the epoch. That's basically our graph. So our Y label will be the negative log likelihood. Just do NNL for short, and then we'll have the title as the loss curve. plt.title as a loss curve. And then we'll show that plot. Basically, it's not that hard to use matplotlib. Look at how easy that is. And now we can start training this model. And we'll see if directly after we'll make the transform to actually have the vocabulary. Have one epoch only, which is nothing. So we're going to have like maybe 10,000 or something. This is like 10,000 epochs. We can have even more than that if we want to train it more. And then we're going to plot the loss curve. And then first, let's see it before we save it. So I'll do 100 epochs to test if it's working. Or 1,000 epochs, we'll do 100 first. Test if this works. Loss curve like this. Okay. Now we'll see what happens. So I'm going to print the epochs here. And it looks like we got an error already. And what we forgot to do is make this Y a NumPy array. It's basically having an int and list. It's looking at how NumPy's operations are and a regular Python list operations are. And then we can use, because we can't use len on that anymore, self.y.size. And let's see if that works. Okay, there we go. We have our 0th epoch, has nothing, and we got our curve. Right here, we have this very high loss, and we have 100 epochs. There we go. It's like linear right now, so that's good. We have like a steady, we're steadily losing loss. We're steadily minimizing our loss, so that's good. Now we are going to try more epochs. Let's just try 1,000 and see how it looks like. And now the loss curve is a little bit more nonlinear, but it's not bad. Still looks a little bit linear, so that's good. And we can actually save the model to a file using pickle. So we'll do with open. We'll make a file for this. Let's call it email classifier. And then we'll make that a pickle file. So pkl, and we'll be writing to the file. Use wb for writing as f, and then we'll just dump it there. Pickle.dump model, and we're going to have the file dumped in there yet. So that is going to be it for that. We'll just have that trained, and let's go check what happens. So I'll just make this go for 10,000, 100,000, or we can just do 10,000 and check what happens. Well, everybody, so we already made this model, actually trained it right now. We did 10,000 epochs. We see that here it went from 3,500 all the way to 929, and we can see that here as well it looks about the same. Our loss curve is correct, and it looks like it's a very non-linear graph now, but it's still kind of steady. You can see we were just kind of like zooming in when we were doing that, like 100 epochs. We were just zooming into here and looking at that section there. That's just a linear. That's usually a normal behavior for machine learning models, so that's not bad for us. That's good. We can save this plot if you want. But there we have it, the model. I might train it. You can train it later again with more epochs to make sure that it has a much lower loss, because this is probably not the lowest it can go. Probably can go much lower, but I'll just keep it like that for now for time reasons. And then now we can actually have actually do some predictions using this model. It might not be the best because we didn't train it for that long. So let's go and make a transform function so we can actually have our model look up the values in the vocabulary list. So I have a presentation on that as well, so you understand how that works. We'll have what's called transforming single documents, because we have a single document that we're going to give to the model, and it's going to make predictions. And our document isn't the same size as the weight vectors we see here. We see that right when we make a prediction, when we make a prediction, we're going to have like something like this, but our X value is going to be different because we don't have all of those documents anymore. We only have one document. So that is going to be a shape mismatch. So that's why we have to be very careful in transforming single documents. So let's go and actually explore this. We already have that vocabulary list to create a mapping, and it's going to be, we already know what it is because we already made it. It's a fixed list that contains all the unique words and their respective TF-IDF score. It's basically a dictionary, actually, because I did update this. It's a dictionary, and it has all of the documents' unique words. That's why you saw it was so easy to create when compared to the IDF. And then each document that you want to transform will be tokenized first. Obviously, we already did that. We already saw how to do that using regex. And each of the tokens will be mapped to their respective tokens in the vocabulary list. So you already saw how the vocabulary list had all those keys. Those are the token names, and then the values. So those are all those scores. And those scores are going to be mapped. So then we can use those scores for actually predictions, because that's the vectorized version of those tokens. And because the document size can change, this might be confusing. Remember, sparse vector means that it will have a 0 in place of tokens that's not contained in there, or to make sure that the size is the same or fixed. Because if the document can be hello, or hello world, or my name is something, we want to make sure they have the same size that is compatible, actually, with the weights. We want to make sure that size is compatible always, so we can do that matrix multiplication and then perform the prediction by having that sigmoid function. To have this sparse vector, we have to have a 0 in place of the tokens that it doesn't contain, but is in the vocabulary list, so we'll have the same size. Now, why is this helpful? It fixes the matrix multiplication errors. I talk about that a lot. It gives us the right TF-IDF, because if there's no other documents, you can't compute it again. It's also not that hard to do. Now, the computational efficiency might not be the best when you think about it first, but the thing is that this is not a list, it's a dictionary. So the time complexity is big O of 1 instead of big O of n, because of it uses a hash table, so each of the keys have hash values. So that's how we can actually do it very fast and have a constant time complexity. You can see that, explore that, how that is, but that's basically how the dictionary is in Python. Very efficient. Now we can try to actually implement it, doing what I said in that presentation. It's not too hard. We already have a dictionary. We can make our transform function, and we'll take in a new document, only a document, a single one. We'll have the raw tokens again, find all of those, what was that same, this is always regex is hard to like make again. You just don't want to It's just something you don't want to do again after you did it once. So I'll just copy paste that. Or you can do it again if you like. And now we can have that same document. We're going to find we're going to basically tokenize the document, have all the raw tokens. And we can do re.ignore case, but it doesn't matter. I'm just having it for redundancy in case I do something to that Redux expression, and I hope the model will still work after that. And now we can have the tokens. We're going to lowercase them, so they're not raw anymore. We'll do the raw token dot lower. Lower is for lowercase always. And we're going to do that for a raw token in raw tokens. This is an easy list comprehension because this is an easy list comprehension because this is just a single document. We don't have to be occupied by the fact that it's a two-dimensional list like we did previously when we were just making this self.raw token to this self.token. So I did it in the wrong spot. Sorry about that. I did it in the other class. That's like a mistake I sometimes do when I have too many classes. So now this is supposed to be here. We have the transform function in this class, not the other class, because if it's part of the TF-IDF. Okay, so now we're going to make a token vector, and we're going to have the self.vocab of the token. We're going to get that value. We get the value of that spot in the keys, because basically, if we see that first, let's go. We have a lot of things now, so I don't want to show this. We can just now comment this out because we're not going to do anything with that. We just print out our vectorizer dot vocab, and we'll see that. I'll show you this so it makes more sense. So we're just getting that key, because it's a dictionary. Remember that vectorizer, remember that the self.vocab is the dictionary. So we see that this is the key, and this gives us a score. We have all of these scores, these TF-IDF scores that we just did like a few moments ago. We calculated these scores here, which was pretty easy, just using these functions. And now we can make that list comprehension using that. And we're going to make sure that that token is in that self.vocab. If it's not in there, then it's going to be 0. The score, we're going to have the score as 0. That means that we don't even care about that word, because it's not significant in the tokens. And this is for our individual token and all of the tokens. And this is the tokens, remember that. And now we can go return these tokens. Make sure that it works. Return token. And we can print out vectorizer.transform. We'll have a document called hello world. Make that simple document, and it will just give us the scores for that. Okay, there we go. We got the scores for hello world. Not anything significant, but if we put like hello world, there is a free iPhone. A free iPhone you can buy, or you can have. And maybe it might be higher for free and stuff, because that's in the training data. So you can see here how big it is now. Look at like 0.5, 0.7, how big those are, and some of them are not even anything. You can see like a U or can have. You can see can is like very low, because if it's in most of the documents, that's you can like play around and look at the scores and how they are. And now we basically have that, but what this is, we notice that the size can still vary. We saw here it was 2. It was of size 2, but we see here it's so long, like so big. So we're going to make it a sparse vector. And now it's going to get complicated. So we're going to have the token vector, call it token vect, or let's make it token vector. And then we'll have that. So now we can get the value self.vocab, and we'll have the key here. And that key will be basically in the items of self.vocab. And that's going to be only if the value is in the token vector. So if the value is in the token vector, else it'll be 0 again for key value in the vocab self.vocab.items. And I don't know if this is going to work, so because it's a very big list comprehension again. So we've got to test it always. Return token vector. We're going to make sure that works. So let's see. We have the transform already. Okay. So it does not work. It doesn't have... Okay, I forgot to have that self.vocab items there. Token vector referenced before in a closing scope. Okay. And I forgot to say that this is a token, not a token vector, because we didn't have that defined yet. Okay, we got it. So we have it, actually. We have this sparse matrix, sparse vector, really. Here it's like very large because of how much vocabulary there is. And we see that it is correct. It has all of, I don't know if it's actually correct, but we should take it as correct. We'll see, actually, if we do the matrix multiplication, if it's correct. Now, what we want to do, one last thing, not delete that. We want to make it a numpy array, so we can actually do numpy operations, numpy dot products. So we'll make that a numpy array. Numpy array token vector. And there we'll have it. And now it's going to be looking better, maybe. It's going to be all collapsed like this. See, we got it. It looks like all of them are 0, but you can see here already that some of them are not 0. Okay. So we made our transform. Now we can make our predict. So we can actually have the prediction. So def predict self, and we'll take in the document. This x is now the document's x, is not self.x, okay? It's the document's one. Now we'll make our y prediction again, and that will be self.sigmoid of, it will be x. The weights are not different. They're now optimized weights. So there we go. And then the predictions, let's just see. Let's just return this y pred first. Let's see what it is. We don't need to map it yet. Let's check if it's actually working. We gotta make sure it actually works. So now we'll have this model. We'll load this model actually, because we already have the model loaded. I'll make like a statement for it later, or I'll make it now, so we don't have to worry about it. We'll have this here stand still. We'll make a try statement. We'll have to make sure that it's not training. We'll just say loading model. We'll print the model's loading, or something similar to that. We'll say loading model, like this, and then we'll have it open that model. What is it? Email classifier. Dot pickle. That's the file, and we're going to have reading. So we're going to use RB for reading, and we'll have it as f. And I'm going to save that model in the pickle.load in that file. Really much of thinking you have to do. You just have to do the syntax. And now we can have some data, whatever data we want. Let's just make this xtest, for example. We'll have a vectorizer dot transform, and we'll have just have like hello, my model is working. This should not be spam. So we'll check what that gives us a score as. Should work. And now we can print out the model.predict for that xtest. And now we'll have an except block if it's not loaded. So except block, and we'll have everything in here in that except block. And you'll print out a training model. Now it should work. We already have this file. Yeah, we do have the file, so that's good. Now we can check if that is working. Okay, loaded the model, and we got the prediction was 0.02. That's very low. That means that it's not even spam. That's very good. We got some good prediction. Now let's go put something very malicious. Let's have something like free offer iPhone buy here. And there could be a link or something. Let's check this out. It might not be correct either. It might not get it. Okay, it's okay. It's 0.5. So it didn't really do it that well, but it's okay. We can have like a threshold at 0.5. This is like a little bit greater than 0.5. And then we can have, I guess it works. Okay. We can try even more. We can have visit this link. Maybe you might not get that. And try and get free laptop. Free is basically a word that comes up a lot. To see, look at that 0.7. It's a very high chance it's spam. And we can try something in the training data, like spam, something here, urgent, free membership, and all this claim and stuff. We can have something like that. We can have like urgent, please claim your free ticket to San Francisco or something like that. And we can see what this says. It should be high. Let's see what it does. 0.8. Look at how high that is. So our model is actually working, and we can train it more and it can work better. And we can have like it print out ham or spam by having the threshold. So in predict, we can make that prediction. We can have the preds variable, and that will be equal to spam if the y-pred is greater than 0.5. We'll just have that as a threshold, and also just be ham, and we can just print out that preds or pred, whatever it is. So now it should give us spam because that's 0.88, and there we go, we got spam. And this is basically how the model is. We can also have a testing set we can do, and we can have that we can have here the test equals to documents message, and we can have it as the int size times 0.2, because now we're looking at the remaining data. And then we can see basically we're not updating that. We have this testing data here. We can actually put this through the model. We'll have a testing labels there also. We'll have label test, label T. We'll have label T, and we'll have that equal to documents label. We'll do the same thing. We'll have that for int size, and we'll multiply that by 0.2 again, and we'll have everything after that. So basically the same thing. We have the test and label test. So now, if we want to do this, we can have a different xt. Now, xt will be equal to vectorizer. And now, yeah, because there's going to be lots of different, this is not for a single document. So we're going to have to use a new vectorizer. So we'll use vectorizer test. Vectorizer t will be equal to TF-IDF of test, and then we can make x test equal to vectorizer test, and then that would just be it, right? Vectorizer test of TF-IDF, yeah. There we go. Let's go print out x test, and we don't need to print out x anymore because we already know that it works. Oh yeah, what do I have here? What was I doing? And this is not even defined, so it doesn't matter. Okay, so we have that. So this is correct. We got that. We got x test working. Now we have to actually give it to the model so I can predict that. So to actually have it give it to the model, we have to make this a list comprehension. And then we have to do it we'll make it a pred is greater than 5 for pred in y-pred. Pred in y-pred. And then let's see, why is this having error? Because we have that. Okay, now let's go and give this to our model. We'll have it predict for x test. It's gonna give us, oh no, it's getting a, okay. It looks like we had an exception, except, we'll see. It looked like it had an exception, so I'll go and see that it's going to change. I hope it didn't change that file. That would be unfortunate. Now, let's see. We have to see what exception we have. That's the downside of using except like this. You can't see like different exceptions or any problems. Now there's a matrix multiplication problem here. Alright guys, so we have a shape error here. So we had a shape error. So I checked, I had to slice X's shape, keeping this the same and making sure that its first dimension has that slice for W shape. And now we get X's first dimension actually compatible with W's first dimension self.W. So now we can actually have this in here. There's something error there, sorry about that. And now we can, we don't need that shape there. And now we can actually get that ypred, make sure that this works. So it's going to give us that whole self.sigmoid. I forgot about that, okay. So basically we can do it like this, because we were actually slicing W as well. We want to have it when you slice X. So now we have all of these probabilities here. We have this actually given, now the preds, the ypred, so we have all the raw probabilities, and now we can actually make that spam in the ham for pred and ypred. So this is what we have. Those are return preds, okay. Okay, we got all of them, so we got ham, spam, all of these, and we can compare now if these are all the same in as the actual Y label or the Y test. We have the Y label test. That was label test, or label T. We can now check if this is equal to label T. So we'll see which entries are not equal. And you can see some are false, some are true, so, but it's not that bad. We did train it with only 10,000 epochs. If you train it with more of them, it's going to be better. But you saw now how to actually make this model from scratch, and you also saw how to fix some errors. I myself had to show you, like I made some errors also while making this. We also made a logistic regression model, gradient descent from scratch. Everything we did with only NumPy and pandas. That's like a big feat, a big achievement. Very good. A pat on the back for you. You did very well. Good job.